So, dear learners, in this session, we are going to learn Maclaurin's theorem. Just we know the contents of M1. So these are the 6 units, and we are in unit number 1. After Rolle's theorem, we are going to consider another theorem. And for that, we also know when do we say that a function is continuous. So left limit must be same as right limit, and same is true for the existence of derivative. Then quickly, differentiability implies continuity, algebraic, trigonometric, inverse trigonometric, logarithmic, and exponential functions are ordinarily differentiable and hence continuous. So addition, subtraction, multiplication, quotient of two or more continuous functions is continuous, and two or more differential functions is differentiable. So with this Lagrange's mean value theorem, the statement is if a function fx is, first condition, continuous in the closed interval a to b. Second condition, differentiable in open interval a to b. These are the only two conditions. Then there exists at least one point C in the open interval a to b such that f dash of c is equal to f of b minus f of a upon b minus a. This is a simple definition of Lagrange's mean value theorem. And if you compare this with the Rolle's mean value theorem, then we realize that there was one more condition in addition to these two, and that condition was f of a equal to f of b. So obviously f dash c will be equal to 0 with the condition that a is strictly less than b, so that b minus a is strictly positive, not even 0. Okay. So Rolle's mean value theorem is a particular case of Lagrange's mean value theorem. And let us see geometrical interpretation of Lagrange's mean value theorem. So we can consider here we have a function represented by this curve. Let us call that function as y is equal to f of x. So here we have y is equal to f of x. Then this is the line x is equal to a, so that the point capital A as coordinates, x coordinate is small a and y coordinate is f of small a. Similarly, this is the line x is equal to b, and the coordinates x coordinate is b, small b, and y coordinate is f of small b. Okay. So with this, and there is a curve which is continuous curve. Then there must be, see this chord AB. So the slope of that chord is going to be, f of b minus f of a upon b minus. We can understand. And as there is a curve, so we can draw so many tangents. So this is one tangent. This is at every point we can draw on tangents. As such, if we are drawing a tangent at C, so you can see. So f dash C is going to be the slope of the tangent at point C, and we can see that the tangent at C is parallel to the chord AB exactly, and thus we can say that here if the curve is continuous at the points A, B, and every point between A and B, and possesses unique tangent at every point between A and B, then there exists at least one point on C on the curve between A and B, such that the tangent drawn at that point will be exactly perpendicular to the chord. So this is geometrical interpretation. And at a glance, again, the same thing is shown in another way. So these things are parallel, and hence f of b minus f of a upon b minus a is exactly same as f dash of c. So this is the thing. Now let us solve some problems. I have brought so many problems here along with some MCQs. So this session is going to be really wonderful and very much useful to all of you. And among Rolle's theorem, Lagrange's mean value theorem, and Cauchy's mean value theorem, I think Lagrange's mean value theorem picks maximum weightage in regard to the importance as well as in regard to the mass. Verify Lagrange's mean value theorem for the function fx is equal to x cube in the closed interval minus 2 to plus 2. So solution is here fx equal to x cube. You know, this is an algebraic function, and obviously it is going to be differentiable, and differentiability implies continuity. So even if you draw the graph of this, so it is going to be continuous in the open interval minus 2 plus 2. Then the derivative is 3 into x square, and in the open interval minus 2 to plus 2, you can pick any value of x. 3 into x square is going to be finite. So we can say that fx is differentiable. So fx is equal to, I must say here fx is equal to x cube. Here fx is equal to x cube is differentiable in the interval minus 2 to plus 2. Thus, fx satisfies all the conditions of Lagrange's mean value theorem. Therefore, there exists at least one point C in open interval minus 2 to plus 2 such that here f of 2 minus f of minus 2 upon 2 minus minus 2 is equal to f dash of C. So I think you have understood. So how to verify further? Just you have to go on putting the values here, and let us see what happens. So 2 to the power 3 minus 2 to the power 3 divided by 2 minus minus 2, that is 4, and that is equal to f dash of c. We know f dash of x is equal to 3 into x square. So f dash of c will be 3 into c square. We have to solve this. So 8 minus minus 8, that is 16 by 4. 16 by 4 is equal to 4, and that is equal to 3 into c square. And therefore, c square is equal to 4 upon 3, and c will be equal to plus or minus 2 upon root 3. Okay. So I think we know that plus or minus both, there are two values of c which are going to lie in the open interval minus 2 to plus 2. And thus, what is Lagrange's mean value theorem? If these two conditions are satisfied, then we are able to find at least one value of c in the open interval, which is uh, part of that open interval. Okay. So thus, Lagrange's mean value theorem is verified. You can take screenshot of this. Initially, I am considering simple problems, then little difficult. Little, that does not mean that it is difficult. Now, yes, verify Lagrange's mean value theorem for the function fx equal to e to the power x in the closed interval 0 to 1. So solution, fx equal to e to the power x is an exponential function, so it remains continuous in the closed interval 0 to 1. F dash x is again e to the power x, and it is finite for every value of x in the open interval 0 to 1. So f of x equal to e to the power x is differentiable in the open interval 0 to 1. So both these conditions are satisfied. Therefore, we can say that by Lagrange's mean value theorem, there exists at least one C in open interval 0 to 1 such that f of 1 minus f of 0 upon 1 minus 0 equal to f dash of 0. Now f of x is e to the power x. So f of 1 is e to the power 1 minus f of 0 is e to the power 0 divided by 1, and that is equal to f dash of c. We know f dash of x is equal to e to the power x. So f dash of c will be e to the power c. That means e to the power c is equal to e minus 1. So c is equal to log of e minus 1. And if we calculate using calculator, log of e minus 1 is coming as 0.5413, and that belongs to the open interval 0 to 1. Thus, Lagrange's mean value theorem is verified. So this is the second example. Many more are further. You can take screenshot. I'm moving within 2 seconds. Next problem, verify Lagrange's mean value theorem for the function fx equal to log of x. So nothing, no base is specified, so we have to assume it natural logarithm, that is basis e. In the closed interval 1 to e, we know value of e is 2.7182, something like that. So solution, fx equal to log of x is a logarithmic function and that is continuous in the closed interval 1 to e. Then if we take derivative of log x with respect to x, that is 1 upon x. And now see, you will understand why do we say continuous in open interval, continuous in closed interval, and differential in open interval. The reason is here in this example. If we allow 1 here, so no, here no problem. If there would have been 0, then it would have been 1 upon 0, that would have been infinity. Even if it is closed, no problem, but the condition is restricted to only open. So for every x in the open interval 1 to e, f dash of x, that is 1 upon x, is finite. And hence we say that f of x equal to e to the power x is differentiable in open interval 1 to e. Thus fx satisfies all the conditions of Lagrange's mean value theorem, and we can say that there exists at least one point c in the open interval 1 to e such that f of e minus f of 1 upon e minus 1 is equal to f dash of c. Let us put the values. F of x equal to log x, so f of e is equal to log of e to the base c, that will be 1, minus f of 1 is log of 1 to any base is 0 upon e minus 1, so that is equal to f dash of c. F dash of x is 1 upon x, so f dash of c will be 1 upon c. So after simplification, that will become, see, log of e is 1. So we can say here 1 minus 0 upon e minus 1. So 1 upon e minus 1 is equal to 1 upon c, and therefore c is equal to e minus 1. And see, it is 2.7182 minus 1. That is going to lie in the interval 1 to e, basically. And thus, we have found at least one value in the open interval such that that equation is satisfied, and hence Lagrange's mean value theorem is verified. Okay, so let us move this to some standard problems. See, these problems are asked. These next two problems, three problems are very, very important. So listen carefully now. Using Lagrange's mean value theorem, prove that b minus a upon 1 plus b square less than tan inverse of b minus tan inverse of a less than b minus a upon 1 plus a square. Hence, deduce that pi by 4 plus 3 upon 25 less than tan inverse of 4 by 3 and tan inverse of 4 by 3 is less than 5 by pi by 4 plus 1 by 6. So you can verify using calculators that the value of tan inverse of 4 by 3 can be found, and the left hand side, right hand side can be found. So that is that inequality is going to turn valid. And this is particular case, but that before that we have to prove the previous statement, prove that. Okay. So here let us try. See this problem, I am repeating this problem, next problem, and also the next problem. These have been asked in the previous university question papers. So very important. Let f of x equal to tan inverse of x in the closed interval a to b. Obviously, tan inverse. So we'll be defining as positive a and b with a is strictly less than. Now we know tan inverse of x is inverse trigonometric function and is going to be continuous in the closed interval a to b. If we take derivative of f of x with respect to x, that is 1 upon 1 plus x square, and we can say that 1 upon 1 plus x square is finite for every value of x in the open interval a to b. So of x equal to tan inverse of x is differentiable in the open interval a to b. So it satisfies both the conditions of Lagrange's mean value theorem. So there exists a point, at least one value c in the open interval a to b such that f of b minus f of a upon b minus a upon f dash of is equal to f dash of c. I think it is very much clear to all of you. And now this is bigger problem. We'll be needing one more screen and see what I have done. So you can see the problem. We did not go back again and come forward repeatedly. So I have taken care of that. So this was the previous screen. So we have to do it this. There exists at least one c such that f of b minus f of a upon b minus a is equal to f dash of c. Remember f of x equal to tan inverse of x. Huh? So f of b will be equal to tan inverse of b. So therefore tan inverse of b minus tan inverse of a upon b minus a. So we have written f of b minus f of a upon b minus a equal to f dash of c. So f dash of x is 1 upon 1 plus x square. So f dash of c will be 1 upon 1 plus c square. Now, if you see what we have to prove here, in the given inequality, the middle portion is tan inverse of b minus tan inverse of a. So let us rearrange accordingly. We can say therefore tan inverse of b minus tan inverse of a is equal to b minus a upon 1 plus c square. If needed, we can give number to this. Okay. And what is the next thing? How to start? This is important. We have said there exists c in the open interval a to b. So that means that a is strictly less than c and c is strictly less than b. So this is the beginning of the next part accordingly. So what we have to see here, we can see 1 plus c square in the denominator. Okay. So let us try to obtain 1 upon 1 plus a square and 1 upon 1 plus b square and compare all these with each other. So a is less than c, c less than b. Therefore, I can say that a square is less than c square and c square is less than b square. Therefore, 1 plus a square is less than 1 plus c square and 1 plus c square is less than 1 plus b square. Therefore, see, 1 upon 1 plus a square. So this will be larger than 1 upon 1 plus a square. Very much obvious. And this will be larger than 1 upon 1 plus b square. Therefore, I can say 1 upon 1 plus b square is less than 1 upon 1 plus c square. That will be less than 1 upon 1 plus a square. Now I am going to multiply all the things with b minus a. Okay. Therefore, as b minus a is strictly positive, so inequality will remain as it is. We know that if we are multiplying by some negative quantity, then the inequality changes. Less than becomes greater than becomes less than. But here b minus a is strictly positive quantity. Okay. So after this, let us see toward this question, equation 1. I am calling this as equation and this as equation 2. Okay. So do not unnecessarily unmute. I have already told you. The recording is going on. So using equations 1 and 2, simultaneously, we can say that here b minus a upon 1 plus b square, 1 plus b square, that is less than. Now see the middle part of equation 2, b minus a upon 1 plus c square, and using equation 1 we can say this is equal to tan inverse of b minus tan inverse of a, and that is less than b minus a upon 1 plus a square. Yes, we have done. But still the problem is not over here. They are again saying, hence deduce that pi by 4 plus 3 by 15 less than this much, and that is again less than something. So we have to take care that. So in this, whatever we have just proved, this is a general and powerful result. Let us call this as equation number 3. So in equation 3, let us put some particular values of a and b. Every time we are going to get new results. So a is equal to and b is equal to. Any idea? So I think that I will put b is equal to 4 by 3. I'm putting b is equal to 4 upon 3, and then tan of pi by 4 is 1. So tan inverse of 1 is pi by 4. That's why I'm putting a is equal to 1. Let us try what happens. So in equation 3, b minus a. Therefore, 4 by 3 minus 1 upon 1 plus b square. 4 by 3 whole square is less than tan inverse of 4 by 3 minus tan inverse of 1, and that is less than b minus a. That will be again 4 by 3 minus 1 divided by 1 plus 1 square. So this is very much straightforward. So please help me. The numerator 4 by 3 minus 1 will
1
be
upon 3.
1 upon 3. Very good. Thank you. Denominator 1 plus 16 by 3. 12. Sorry.
25 upon 9.
1 plus 16 upon 9. Na?
25 upon 9.
Very good. S25.
Yes, sir.
Less than tan inverse of 4 by 3 minus tan inverse of 1 is
45.
pi by 4.
Pi by 4.
Pi by 4.
And that is less than 4 by 3 minus 1, again 1 by 3, and divided by 1 plus 1, that is 2. And now what I am going to do? I am going to add plus pi by 4 everywhere. So here I am going to get pi by 4 plus So it will be 3 upon 25. 3 upon 25 less than pi by 4 plus tan inverse of 4 by 3 minus 4 pi by 4, that is tan inverse of pi by 4, and less than pi by 4 plus 1 upon 6. That's all. So finally we have done it correctly. So please take screenshot. 5 seconds. This problem is asked in exam so many times. Now two more big problems and then 2-3 small MCQ problems, that will be the end. So this is really on Monday. This is our beginning of a fresh week and we are doing it smartly. We are utilizing it in the best possible way. So here, using Lagrange's mean value theorem, prove that b minus a upon square root of 1 minus a square less than sine inverse of b minus sine inverse of a, and that is less than b minus a upon square root of 1 minus b square. So let us try to see. Here f of x equal to sine inverse of x. This is defined in the interval, close interval a to b. We can understand. Now see, now sine of anything, you know sine wave. Sine wave is known to you. So it always, you may have x versus y. Y is equal to sine of x. So you can put any value of x, y will be always lying from -1 to +1. But still, let us say here from 0 to 1 for our convenience. No problem, 0 to 1, so that it will not be any confusion. Now f of x equal to sine inverse of x is inverse trigonometric function and is continuous in the open interval a to b. Then f dash of x is 1 upon square root of 1 minus x square. So here x is for every value of x from a to b. Okay. Then therefore f of x equal to sine inverse of x is differentiable in open interval a to b. Thus fx satisfies all the conditions of Lagrange's mean value theorem. Hence there exists at least one point C in the open interval a to b such that f of b minus f of a upon b minus a is equal to f dash of c. Okay. So please help me now. We have written where to solve it further. F of x equal to sine inverse of x. So f of b will be equal to sine inverse of b minus f of a. That will be sine inverse of a. F of b minus f of a upon b minus a is equal to f dash of c. Now f dash of x is 1 upon square root of 1 minus x square. So f dash of c will be 1 upon square root of 1 minus c square. Okay. So here, whatever is to be proved, in the center we see sine inverse of b minus sine inverse of a. So we'll try to write in that form. So we have to multiply this equation by b minus a. So sine inverse of b minus sine inverse of a is equal to b minus a upon square root of 1 minus c square. Okay. So let us call this as equation number 1. We have done it. Then also, we have been always saying C belongs to the open interval a to b. That means a is strictly less than c and c is strictly less than b. And what we have to do? We have to find relation among 1 upon square root of 1 minus c square, then 1 upon square root of 1 minus c square, and 1 upon square root of 1 minus b square. So let us start here. Let us square these things. So a square will be less than c square will be less than b square. Now let us multiply by minus 1. So minus a square will be greater than minus c square. Minus c square will be greater than minus b square. Fine. Let us add 1. So inequality will remain the same, like this. After that, take square root. So positive, we'll be considering only positive square root, like this. And after that, we have to take reciprocal. So 1 upon square root of 1 minus a square, this will be less than 1 upon square root of 1 minus a square, this will be less than 1 upon square root of 1 minus b square. Okay, that is fine. Then in the next step, we have to multiply this by b minus a. Because in the right hand side of equation 1, we see b minus a upon square root of 1 minus c square. So let us multiply by b minus a. This is strictly positive. So inequality will remain the same. Therefore, b minus a upon square root of 1 minus a square is less than b minus a upon square root of 1 minus c square less than b minus a upon square root of 1 minus b square. So if you want, you can give equation 2, equation number 2. So comparing equations 1 and 2, equations 1 and 2. So equation 2 starts with b minus a upon square root of 1 minus a square, and that is less than b minus a upon square root of 1 minus c square. Using equation 1, we can say that is exactly equal to sine inverse of b minus sine inverse of a, and that is less than b minus a upon square root of 1 minus b square. And thus, this is what we wanted to prove. So hence the proof. Please take screenshot. And again, additionally, something is asked, hence deduce that. So accordingly, you can identify the particular values taken by A and B. Put, then simplify, you will get the required results. Okay. One more big problem, not so big. Using Lagrange's mean value theorem, prove that 1 minus A upon B less than log of B by A less than B by A minus 1. So let us see solution. Here f of x equal to log of x. Let us define in the interval, close interval a to b, where 0 less than a less than b. Because we know that log of 0 is minus infinity and log of negative quantity is never defined. So we are saying a is greater than 0 and b is greater than a. Here fx equal to log x is a logarithmic function and that is continuous in the closed interval a to b. Dash of x is 1 upon x and that exists for every value of x in a to b. That is the reason we have said here 0 is strictly less than a. Otherwise, if we would have said that 0 less than equal to a, and if I say here close interval, then 1 upon 0 would have been infinity. So in that case, f of x is not differentiable at x is equal to 0. Okay, so a is strictly greater than 0, and hence if x is differentiable in the open interval a to b. Thus, Apex satisfies all the conditions of Lagrange's mean value theorem. Therefore, there exists at least one point C in the open interval a to b such that f of b minus f of a upon b minus a equal to f dash of c. Now you have to please help me to solve this further. So again, please can you tell me f of b minus f of a upon b minus a. What is f of x? F of x is, have you forgotten? See, everything is in front of you. F of x is log x. F dash f is equal to 1 upon x. So f of b, what will be f of b?
Log B.
Log b.
B
Yes.
Log B.
Minus
minus log
f
E.
of a means log
Log
of
A.
Log A.
upon b minus a.
B
That
minus
is equal to f dash of c. F dash of c means, please tell.
1 by x.
1
by
by
1 upon C.
1 by
See,
C.
f dash of c. F dash of x is 1 upon x. So f dash of c will be 1
1 by
upon.
C.
1
upon
upon C.
Okay. So let us try to simplify this. This is very easy. Log of b by a upon b by minus a is equal to 1 upon c. And see what we want to prove. At the middle there is log of b minus a, and therefore let us keep log of b minus a at one side, and that is equal to b minus a upon c. That is fine. This is called, let us call this as equation number 1. Okay. We know the relation among a, b, and c. We know that a is strictly less than c and c is strictly less than b. Now, what further? What is to be done? Okay. पुढे काय करायचं सांगा मला. I'm not going to do anything now.
Square.
Square नाही. हे बघा ना. हे बघा.
B minus C. Log B.
So see, equation 1 right hand side काय आहे? B minus A upon C है ना. So C is in denominator ना. So everything is to be taken in denominator. 1 upon A, 1 upon C, 1 upon B. Please tell me now. Greater than or less than? Please tell.
Greater than.
Greater than, sir.
Greater than. Greater than.
Change.
Now B minus A. B is strictly greater than A. Na? So B minus A is strictly positive quantity. When we are multiplying with B minus A, inequality will remain the same. B minus A upon A will be greater than B minus A upon C, and that will be greater than B minus A upon B. So let us call this as equation number 2. And therefore, using equations 1 and 2 simultaneously. So here, actually, again, I will say that this is B minus A upon B less than B minus A upon C less than B minus A upon A. Okay. So this is equation number 2. Now, therefore, B minus A upon B is less than B minus A upon C. In equation 1, B minus A upon C is equal to log of B by A. And again, from equation 2, that is less than B minus A upon A. And therefore, B minus A upon B is 1 minus A by B. So I am putting in bracket, that is less than log of B by A, and this is less than B minus A upon A, that is B by A minus 1. So hence the proof. Please take screenshot. So we have solved many problems. Still, I know there are chances that there will be online exam. So which type of problems will be there? 2-3 problems of that type, and then we are going to pause for one day. Okay. So here, according to Lagrange's mean value theorem, fx is continuous in closed interval a to b, differentiable in open interval a to b, then there exists c belonging to open interval a to b such that. So what is the correct answer? Please tell.
A.
A is the correct answer. A.
A.
f dash. So after taking so many efforts, everybody can quite easily tell this is A. Next MCQ problem. So this is for your convenience, and problem is here. If fx equal to x into x minus 2 defined in 1, 2, 3 such that f of 1 equal to minus 1, f of 3 equal to 3, then according to Lagrange's mean value theorem, C is equal to, options are provided. Please put and tell me answer immediately. Solve and tell me. So that will be f of 3 minus f of 1 upon 3 minus 1 is equal to f dash of C. Okay. What is f of 3? It is given, no necessity to calculate. Okay. Even if calculate 3 into 1, that is 3. What is f of 1? 1 into minus 1, that is minus 1. Divided by 2 is equal to. Now f of x is equal to x square minus 2x. So f dash of x, derivative of x square is 2x minus derivative of 2x will be equal to 2. So f dash of c will be equal to 2 into c minus 2. And therefore, see 3 minus minus 1, that is 4. 4 by 2 is 2. 2 is equal to 2c minus 2. Divide through it by 2, that is 1 is equal to c minus 1. And therefore, c is equal to 2. This is the correct answer. So as such problem will be for 2 months. Already you are given f of 1 equal is given f of 3, no necessity to find. I have already told, whenever there is MCQ problem, original problem is broken into 2 or 3 parts and only one part is asked. If the part is very easy, the question is for 1 mark. If problem is little difficult, that is for 2 marks. This is going to be our strategy. Remember this. In the next, you have to answer me. Tell me. F of x equal to x square defined in closed interval 1 to 5 such that f of 1 is given, f of 5 is given. Then by Lagrange's mean value theorem, C is equal to, tell, everybody must tell now. No one?
Option B, sir.
3? Do you want to say 3?
B, 1.
B, huh? Let us just try. Let us verify, huh? So f of 5 minus f of 1.
D.
Okay, let us solve this. So is there any person who is going to promote option A and C? And that is equal to f dash of C. Now see, f of 5 is 25. F of 1 is 1 upon 4. That is equal to f of x equal to x square. So f dash of x is equal to 2 into x. So f dash of c will be equal to 2 into c. Therefore, 24 upon 4, how much? 6, na? Sorry, 6. That is equal to 2c, and therefore 3 is equal to c. C is equal to. So D is the correct option. Yes. I am moving further. Let us see whether we have finished or not. Yes. It's question time. Any question? It was a very nice session that you were listening very much sincerely. Thanks for the attitude. Yes, attitude. Attitude is everything. Nothing. No talent. We do not want talent. We just want attitude. Yes. So I think that there is no any question. Thank you very much.